Now, a lot of chemistry is done in solution instead of the gas phase. And so we have our equilibrium constant in terms of the pressure. Let's look at how we can express the equilibrium constant in terms of concentrations in solution. So say we have a reaction where A and B are in equilibrium. So we can write the equilibrium constant in terms of pressure as the pressure of the product, B, raised to its stoichiometric coefficient, divided by the pressure of the reactant, raised to its coefficient. So these are pressures. I'll use the ideal gas law. I can write pressure as nRT over V. So this is the number of moles of product B. And I'm raising all this to the B power. And then I have the same thing for reactant A. I'll write it in terms of the ideal gas law. And then I'll notice that N over V is concentration. It has units of moles per liter. So that's molarity. So I can write the molarity of B raised to the B power times RT to the B power. So I'll write this as molarity. Then I'll have the molarity of reactant A, moles per liter. So I have the molarity of A raised to the little a power times RT to the a power. So now this right here is the concentrations of the product over the reactant. So this is what we call the equilibrium constant in terms of concentration. So this would be K sub C. And then what we have left over is RT to the B minus A power. So we can write our equilibrium constant in terms of pressure is equal to the equilibrium constant in terms of concentrations times this factor. So remember, B and A are the stoichiometric coefficients in the balanced equation. So this is the way we can convert the equilibrium constant in terms of pressure into one in terms of concentration. So if I solved for Kc, I would have Kp times RT to the A minus B power, just the negative of this difference. So I can convert one to another from pressure to concentration. Now you'll notice that I wrote it in my abbreviated form. I haven't divided by the standard pressures. We'd have to divide by standard concentrations to get the units to cancel, but I didn't want to complicate it too much, so I wrote it in my abbreviated form. And so this is the equilibrium constant in the abbreviated form, and so we're just, remember, dividing by standard concentrations, 1 molar, so that these units will cancel. I'll have factors of units for RT to cancel those units as well. So, but this is our abbreviated form, and just remember that this is unitless. We'll have concentration units, RT units, but just remember that in our abbreviated form, all our units are going to cancel. So let's do an example of converting between pressure and concentration units for the equilibrium constant. Let's consider this reaction. The dimerization of nitrogen dioxide, and we measure Kp, and it's 10 at 400 Kelvin. We want to know what the equilibrium constant is in terms of concentration. So you remember, we can write this as so I had it written as B minus A, but for the balanced equation, number of moles of product minus reactant. So I'm going to write it as delta N, where delta N is the number of moles of gaseous products minus the number of moles of gaseous reactants. And so if I want to solve for Kc, it would be Kp times RT to the negative delta N, because I'm taking RT to the delta N over to the left side of the equation. Okay, so delta N is the number of product moles minus reactant moles. So I have one product, two reactants, so it's 1 minus 2. So delta N, in this case, is equal to 1 minus 2, which equals to negative 1. So Kc would be equal to Kp, which is 10 times RT to the negative delta N. So delta N is negative 1, so the negative of that is 1. So Kc would be equal to 10. Now these units for R came from the ideal gas constant when we formed the equilibrium constant, and it was in terms of pressure units. So it's going to be 0.0821 liters, atmospheres, moles, Kelvin. I really don't need to write the units because all the units are going to cancel anyway. So my temperature is 400 Kelvin. So this would be the value of Kc is 328 at 400 Kelvin, where Kp was 10. So now the form of the equilibrium constant, remember, is the amounts of products of reactants. So Kp is the pressure of N2O4 raised to the first power divided by the pressure of reactant NO2 raised to the second power. So that's Kp in our abbreviated form. And Kc will be the concentration of N2O4 raised to the first power divided by the concentration of the reactant NO2 raised to the second power. So these are the forms of my equilibrium constants, and this has a value of 10 for Kp, and Kc has a value of 328.